Howdy, howdy. This is Mr. Potter. Welcome to day 2 of our discussion on limits. Today we're going to go a little bit into a different vein of limits. We're going to be looking at algebra to help simplify our limits. We're also going to be talking about one-sided limits, and we're also going to do a discussion of the Sandwich Theorem and a couple of examples of these problems. So the first thing I want to talk about today is I want to talk about using algebra. Now, when we talked about graphing rational functions, we always introduced the possibility of having vertical asymptotes. And of course, any time that I divide by 0, whenever my term ends up being 0 in the denominator, I run into that risk of hitting a vertical asymptote. However, this one is a special case here. And it's a special case because the numerator factors. This is a difference of cubes. So this is going to factor to x minus 2 times the expression x squared plus 2x plus 4. And so when I've got this in the denominator, what I really have is a term that I've got a common factor in the numerator and the denominator. And in an algebra sense, I can think of these terms dividing out. But in reality, I can't. I still have the restricted domain that x cannot be equal to 2. But if I want to talk about this from a limit standpoint, the limit as x approaches 2, I really have a hole here. The fact that I've got a common factor in the numerator and denominator, a common factor which would divide out if I did division, gives me a polynomial, in this case a parabola. And as x approaches 2, x is going to traverse along the path of the parabola. So y is going to be described by this parabola, except for the hole at x equals 2. So if I want to evaluate the limit of x cubed minus 8 over x minus 2, that's going to be equal to the limit as x approaches 2 of x squared plus 2x plus 4. These are going to have the same limit even though they don't have the identical graph. The graph for my rational function will look just like my parabola, except I'll have a hole where x equals 2. And that hole will be wherever this limit says it is. So this is going to be 2 squared plus 2 times 2 plus 4, or 12. So this hole is going to be at the point 2, 12, and my limit here is equal to 12. And I want to compare that to this function here. This function is a completely different situation because if I try and factor notice that I do not have a common factor in the numerator and denominator. And in fact, because there's no way for me to eliminate this x minus 1 factor in the denominator, I'm going to have a vertical asymptote at x equals 1, because it's the value of x that makes this undefined. And if I take a look at the limit as x approaches 2, I mean, the limit as x approaches 1 of this function, because I've got that asymptote, this is one of those situations where the limit does not exist. And in fact, when I look at this from a graphical standpoint, I'll see that I've got an asymptote that goes down for values less than -1. I mean, less than +1. And goes up for values that are greater than +1. So, looking at this, the fact is that if I have a common factor in the numerator and denominator, then there's a chance that the limit can exist. And of course, I say can because in this case, I could eliminate the entire denominator, any aspect of the denominator that would make the denominator 0. If I can't eliminate that, then even though they have a common factor, the limit still won't exist. But in this situation where I had the x minus 1, if I don't have a common factor, then I'm going to have the vertical asymptote, and I'm not going to have a limit. So this is what we have to deal with rational functions. I run the risk of having a situation where I have a vertical asymptote instead of a limit. So next we want to talk about the step function. The step function is a function where I'm dealing with the greatest integer function, the greatest integer that's less than or equal to a particular integer. So if I were to take a look at 1.5, well, the greatest integer that's less than or equal to 1.5 is 1. Even if I go up to 1.9, the greatest integer that's less than or equal to 1.9 is 1. And I can continue this as much as I want to, until I actually reach 2, because 2 is an integer, and the greatest integer less than or equal to 2 is in fact 2. So what happens is I have these series of steps where I'm closed interval on one side, but open intervals on the other. And what happens here is I can talk about the limit at any of these interior points, any point between 0 and 1, any point between 1 and 2. But when I talk about what happens at 2, I run into a little bit of a problem, because for values less than 2, this seems pretty constant towards 1. And if I'm looking at values to the right of 2, I've got values that are pretty constant at 2. So it really makes sense to talk about a one-sided limit, an idea of describing the function as x approaches 2 from its left. And in this case, that's going to be 1. But I can also talk about the limit as x approaches 2 from its right side, from the positive side of 2. And if I look at the greatest integer function there, I do in fact get 2. So we have this idea of one-sided limits. When I'm dealing with one-sided limits, I either am looking at the value as x approaches c from the left side, in other words, from its negative side, or as the limit as x approaches c from its positive side. And I can end up with 2 wildly disparate answers here. So the idea is I want to look at values that are less than c. In other words, I'm really only looking at values to the left of the point in question. Whereas over here, I want to look at values that are greater than c. In other words, values that are to the right of my function. And I want to get as close to it without touching it, just like our window example that we talked about. But if I'm looking at limits from the left, I really only care about what happens over here. I don't care what happens to the right of my window frame. And similarly, when I'm looking at limits from the right-handed limits, I'm interested in what's happening in these 2 quadrants and don't care what's happening for values that are less than c. So this is our idea of one-sided limits, and it brings up an interesting idea. The thing is, if I have that the limit as x approaches c from the left of my function is equal to 1 number, and the limit as x approaches c from the right of that same function ends up being the same number. Because L is equal to L, I can say that the limit exists because I've got it approaching a number from the left. I've got it approaching a number from the right, and it happens to be the same number. So I can say that the limit at this point exists. So a limit exists when three things happen. One, the left-handed limit exists. It is equal to some number. Two, the right-handed limit exists. It's equal to some number. And three, those aforementioned numbers have to be equal to each other. So I can't have two distinct numbers as I would have had for the step function. Here, from the left, as I approach 2, my values are equal to 1. Here, as I approach from the right, my values are 2. But if I was instead to look at this, the limit as x approaches, say, 1.5 from the left, and the limit as x approaches 1.5 from the right, these both happen to be 1, because I'm approaching 1.5 from the left, and from the right, I'm on the same line segment. So both these limits do exist and are in fact equal to each other. So I can say for my step function, limits exist at every non-integer. So I want to go through another example of dealing with when do limits exist. So I've got this convoluted piecewise function, and for each of my lattice points, I can talk about what happens as x approaches 0 from the left, and as x approaches 0 from the right. As x approaches 1 from the left, and as x approaches 1 from the right. So I can take a look at each of these points. If I wanted to try and evaluate this, I'm going to run into a problem, because values of x that are less than 0 aren't in my domain. There is no graph here. So I can't say that this limit exists. So this limit does not exist. But for values of x that are slightly larger than 0, slightly larger meaning I'm on this path trying to head towards 0, I am in fact approaching a particular y value. I'm approaching a y value of 0. if I'm looking at x approaching 1 from the left side, I'm on this path heading towards 1. And I'm noticing that my y value is getting closer to 1. And as x approaches 1 from the positive side, x is also approaching 1, y is also approaching 1. And I notice that these are equal, so at x equals 1, the limit exists. It didn't exist at x equals 0 because it failed that first step, that the left-hand limit doesn't exist. And it's pretty obvious I'm going to have that exact same problem at x equals 4 because my right hand doesn't exist. Now, if I'm looking at what happens when x approaches 2, I've got the limit as x approaches 2 from the left of my function. And because I'm on this constant function, that's going to be 1. But if I take a look at the limit as x approaches 2 from the positive side of my function, I'm actually down on this curve heading towards x equals 2, and it's equal to 0. So this is actually the third case where a limit would fail, because the left-hand limit exists, the right-hand limit exists, but they're not equal. So I can see how a limit would fail by looking at this example. This actually illustrates all three examples. And the limit does exist at x equals 3 because my function in both of these cases are approaching y equals 1, even though my function is defined to be y equals 2. My limit is the path on the curve heading towards x equals 3, both from the left and from the right. And of course, since I'm approaching the same value, this limit does exist, where this limit does not exist because of rule 3. So this kind of is, in a nutshell, what we're dealing with when we talk about left side limits and right side limits. This really does illustrate many of the major points. So the last thing that I want to talk about in this video is the idea of the sandwich theorem. And when I'm dealing with the sandwich theorem, I'm looking at this with three functions: f of x, g of x, and h of x. And two of these functions I know rather well. They're pretty well behaved. The question is, what happens with g of x? This is the function that I don't know much about. All I do know is that I've got this boundary situation where f of x is always less than or equal to g of x. And h of x is always larger than or equal to g of x. Now, it may be easy for me to determine the limit as x approaches c of one of these functions. And it may be easy as x approaches c for me to find another function. But my question is, if these are equal, in other words, if these are both equal to L, because g is trapped in between these functions, and I do have a top function h of x, I have a bottom function f of x, and of course g of x has to lie somewhere in between, but it kind of gets pinched, it kind of gets stuck in here, like a sandwich where I've taken my fingers and pressed the bread too hard. The meat and the cheese kind of get merged together. And so what happens is this limit also has to be L. So the idea is that if f of x, g of x, and h of x are in this order, and I know the limits for f of x and h of x at a particular point, and they happen to be the same value, then g, by its very nature of being sandwiched between f and h, has to achieve that limit as well. And so I'm going to go through an example of this. I've got the limit as x approaches 0 of x squared times the cosine of 1 over x squared. And so I want to start by talking about the behavior of cosine theta. We know from pre-calculus that cosine theta is a pretty well-behaved periodic function. It's always bound between -1 and 1. And in fact, whenever we're dealing with sine and cosine, this is an assumption we can make. No matter what my angle is, no matter what theta is, cosine's very nature causes it to be bound between -1 and 1. And this is almost like the function that I'm dealing with. Almost, because I'm neglecting this x squared. But it's certainly possible for me to distribute through to multiply every term by x squared. And so what I've got is I've got my mysterious, ugly, awkward function bound between two rather nice functions. X squared, which I know is a parabola, and negative x squared, which is its opposite. So now if I want to take a look at the limit as x approaches 0 of each of these three functions, I've got a pretty nice polynomial here. I've got this ugly question that the target of our discussion in this case. And I've got another rather nice polynomial. And one of the things we talked about last time was that if I have a polynomial, I can do a direct substitution. 0 squared is 0. And 0 squared is 0. So certainly the opposite of 0 squared is 0. And so I end up with this situation where my limit, the question at hand, is a value stuck between 0 and 0. And the only number that satisfies this inequality is itself 0. So I can say with pretty much definite understanding that this limit must be equal to 0. And so this allows me to work with limits, especially with periodic functions. That's one of the main tools of this sandwich theorem. But the idea is that if I have these functions, that I have a good understanding of their range, I certainly can use that to my advantage to come up with functions that are fairly well behaved. Functions who I can evaluate their limits fairly easy. And functions whose limits should be the same. So that's the sandwich theorem in a nutshell. So I'm glad you've enjoyed this discussion of limits. We'll be talking more about these in class. Once again, I'm Mr. Potter. Have a wonderful day.